This is the rest of chapter 7 notes. Like I said, quick chapter. I know I've been going kind of fast. Sorry about that. But remember, I'll put the PowerPoint without me talking. So if you need to go through stuff, just to this part just goes through the families. And again, a family or group is a column on the periodic table, and they have similar properties. And again, because they have the same amount of valence electrons. So the alkali metals is the first row, except or the first column, except for hydrogen. So this is like lithium, sodium, potassium, those guys. Okay, they are the alkali metals. They're super, super soft. I mean, you can cut them like with a scissors. They're not found naturally. You cannot find them in nature because they're so reactive. They react with air, they react with water. So you will always find them in combination with something else. If you want to get them in the pure form, you have to go through a chemical reaction to reduce them into their pure form. And you actually store them in oil, because if you leave them out, they'll react with air. Okay, they have a little shininess to them. Okay, and they're very good conductors, so they're typical metals that way. They're softer than most metals you think of, but again, they're super, super reactive. Okay, they have very low densities. So here you can see, here's lithium where they melt. Their densities are really low, less than water. So all these guys, would float in water because, except rubidium and cesium, they would. Water's density is 1. So you can see that. And again, they have these guys. If you have some of them, well, like if you have a piece of sodium, which is a common thing that they have in lab, that would melt in your hand, but it would also burn your hand because it would react with it. Okay, so alkali metals have low densities and low melting points, low ionization energy. In other words, it doesn't take much energy to take away their electron because they only have 1 on the outside. The choice is give up 1 or pick up 7. They're going to give up 1. Okay, and here you can see, here's water. When you add lithium to it, reacts, it kind of fizzes. Look at sodium, actually burns a little bit, and potassium will start on fire. If you take a piece of potassium and put it on an ice cube, the ice cube will start on fire. So of these ones, potassium is by far the most reactive, but they're all super reactive. As soon as you put them in water, they go zoop and they're gone. Okay, so they're very, very reactive and they're very exothermic. There's a lot of heat given off when they react. Again, potassium is the most reactive of all of them. Sodium's pretty good too, though. Sodium's pretty good. Okay, I talked a little bit about this with flame tests. Flame tests is when you have your electron and it's supposed to be like here. Let's say it's supposed to be in the 3s. And you heat it, so you give it energy, so it bounces up here to the 3p, but it knows it's not supposed to be there. So when it goes back down to where it's supposed to be, goes back down to its ground state, it has to give off that energy absorbed. And each element has a characteristic wavelength of energy they give off. So if you do lithium, if you take a lithium, and usually you can put it in a compound, it can be like lithium chloride, lithium nitrate, whatever. But when you burn it, it gives off this color. That is the wavelength of the light from it going back down to here. Okay, sodium is bright orange. Potassium's kind of cool. It's kind of a lavender color, but they have a characteristic color and it's based on the wavelength of the light that's given off when they jump up. Okay, so and it's because you give them energy and they jump up here. They know they're not supposed to be here, so they want to go back down to their ground state. When they want to go back to the ground state, they have to give off that energy. And the energy of each element is a certain wavelength, a certain color. Okay, the alkali earth metals, this is going to be beryllium, magnesium, calcium, strontium. Their configuration, if you do the noble gas, is the same, because that means they have 2 valence electrons. Their melting points are higher, the density is a little bit higher. But they're still pretty reactive, Their ionization energies are low, again, because they have 2 electrons in the outer. They're looking for 8. Are they going to pick up 6 or are they going to give up 2? They're going to give up 2. So again, metals are very, very giving, okay? They'll give up their electrons. And again, they become cations with a +2 charge. They have to lose 2 valence electrons in order to be stable, okay? The alkali earth metals, beryllium doesn't react with water, but the rest of them do. Magnesium, it has to be really hot, and the rest of the guys. So you get more variety. The alkali earth metals are very similar in all their characteristics, whereas the alkali metals, sorry. The alkali earth metals, one step over there, you got a little variety going on there, okay? So beryllium won't react with water. Magnesium, it has to be really hot, has to be steam, and the rest of them will just react with water, okay? So reactivity of these elements increases as you go down. And again, it's because the electrons are farther away from the nucleus, so they don't have as much pull on them, so they'll react faster. Okay. There's oxygen family is oxygen, sulfur, selenium, beryllium. Oxygen has what they call allotropes. It means it can exist in different forms. We have O2, which is the most common. I mean, if you work in any healthcare fields, you've heard of O2 before, dioxygen. That's the way oxygen is in its pure form, it's diatomic. There's actually O3 as well. That's ozone. Anytime you've ever, if you've plugged something in and it like electrocuted you, you got that sharp, I don't know, it's an odor almost. That's ozone. And the weird thing about ozone is up in the atmosphere, it protects us. It's a layer that knocks out some of the UV rays. And you've probably heard our ozone layer is thinner now than it used to be. That's why we have more skin cancer and people have to wear sunscreen and all that other stuff. Okay, that layer up there is really good for us. But when it's down here, it's on Earth and we breathe it in, it's actually a pollutant. So we like it way up in the atmosphere, but we don't like it on Earth. Okay. The halogens is the group 7. These guys, again, it's fluorine, chlorine, bromine, iodine. These guys are the salt formers. Okay. They are very, very, very reactive. The most reactive nonmetal is fluorine. And they want 1 electron. They got 7. They need just 1. Just 1 more. I got this. So they are very reactive. They have high electron affinities. They really, really want electrons. Okay. They exist as anions. In other words, they exist with a negative charge. -1 is their standard charge. That's how they exist in nature. But if you put them with a metal, you're going to get metal halides, you're going to get a salt. Okay, and when I say salt, it's not just sodium chloride. It could be sodium iodide. It could be potassium bromide. Those are all considered salts. And a salt is a metal and a halogen. Okay, the noble gases, again, is the group that's stuck up. They don't react with anybody. And the reason for that is they have a full outer energy. They don't need anybody, okay? They're good. All right, so they don't react with other things. The bigger ones like radon and xenon do a little bit because, again, you've got a really big molecule, so, I mean, a really big atom, so it's kind of easier to sneak away an electron or two. But these guys, helium, neon, not going to happen. They don't react with anything, okay? Their electron affinities are positive. In other words, they're opposite of what everybody has. They really don't, they're not going to form any anions, okay? They're not going to react. So they're really unreactive. And again, they have a reason for it. They already have a full energy level. They're full, they're good, they don't need anybody else. They want to be by themselves. Okay? And most of the time you'll find them in their monatomic. In other words, helium, you just find it as He and neon as Ne. Again, they're not diatomic like oxygen and nitrogen and hydrogen, all that. They don't need to be stuck with anything else. Okay? Hydrogen, again, hydrogen is a weird element. It's the first element. It's 1s1. It shouldn't be over there with the metals, but it is because that's where it fits in the periodic table. So it has a metallic electron configuration, but there's nothing about hydrogen that's metallic. Okay? It's what makes things acids. If it has hydrogen in front, it's an acid. Okay? So hydrogen doesn't follow the rules. Hydrogen can become an anion or a cation. It's one of the, there's a few others that'll do that, but hydrogen is, notorious for stuff like that. So that's it. We're done. We're done with chapter 7, and now it's time again to get ready for your unit 3 test.